Hi guys, let's talk about how to draw magnetic fields and current carrying wires. Even if you don't know the math and you can't do the vector multiplications, you can still use a trick called right-hand rule to be able to figure out and then draw the direction of the magnetic fields. Now for straight wires, what we're starting out with, you start out with your right hand, put your thumb in the direction that the current is going, and your fingers will literally curl the way the magnetic field. Here, you can see that I would curl around the back. Now, it's a two-dimensional paper, so I can't do that. It would curl around the back and over the front with my thumb pointing upwards. So in other words, the magnetic field would look like this. Now, whenever you're drawing it, be careful drawing three-dimensional. You want to cross over the wire and then go down behind the wire, making it disappear behind the wire. Notice I'm crossing over and then trying to make it disappear by leaving a gap over the wire. And I'm nowhere close to the best drawer in the world, but I can still at least try to get that idea. Now notice how that works. My hand dips behind the wire and curls around the front with my thumb pointing upwards. And then likewise with number 2, my thumb points downwards with the wire, and my fingers would curl down around back this way over the top of it. So it's going to go the opposite way here, like this. And then the magnetic field would go literally everywhere, all up and down the wire, wherever there was the current carrying, because we already found out that whenever charges move, we get magnetic fields, and current is moving charges. For number 3 and 4, it's the exact same deal, just now I have to deal with the fact that it's going right or left. Thumb pointing in the direction of the current for number 3, so I'm going to end up curling down behind and over the top. So I'm going to come over the top like this, and then curl back behind. There, back behind and over the top. Number 4 is the opposite. Fingers curled this way with my thumb pointing to the left here. So I'm going to go over the top and then back down behind. Notice how it's actually the exact opposite from the previous one, from number 3 up here. Number 4 is exactly the opposite. Now, something that you might not have seen is this idea of a wire coming into the page or out of the page. This is just a notation that we can use whenever we have a three-dimensional object trying to be shown two-dimensionally. Imagine an arrow tip coming out of the page, an arrow coming at you. Somewhat of a scary thought, so please don't continue down that thinking. But out of the page, arrow tip coming at you. So I take my thumb, current coming out of the page, and I point it upwards there, and my fingers show me which way it would curl. The magnetic field goes around circular this way, counterclockwise. So my magnetic field, I would end up drawing like this. And of course it would get weaker the further out we go. There, we would notate that by the field lines becoming further and further apart. Number 6 here, it's going into the page, kind of like the tail feathers of an arrow. So I'd put my thumb going into the page and notice that my fingers curl clockwise. Now, that's how we're going to end up doing straight wires. Right-hand rule, put your thumb in the direction of the current, and the direction your fingers curl is for the magnetic field. Solenoids, or coiled wire that has current going through them, is similar in the right-hand rule, but slightly different, and in fact somewhat opposite, of how we would apply it. Here, I'm going to curl my fingers in the direction the current goes around the loops, and then I'm going to see where my thumb points. That's the direction of the magnetic field inside of the coil itself. Notice how in these I have tried to draw three-dimensionally. It looks like, in this case, the current comes out of the battery and then starts out disappearing back behind and then comes around in front. It disappears behind, comes around in front, disappears behind, and then comes around in front. Almost like the current is looping. Notice I was saying around in front, that the current's going kind of like this here the entire time, up and down and around. So here, for my magnetic field, I'm going to take my hand, my right hand, I'm going to curl my fingers now in the direction the current's going since it's looped. It's dipping down behind first and then coming around in front. Dipping down behind first. Notice here the dipping behind the gap in the wire. So dipping behind and then back around in front. And my thumb shows which direction the magnetic field points inside of the wire. Inside of the wire, the magnetic field, B, is pointing to the right, or excuse me, to the left here. And then, of course, whenever it exits, it would loop back around. Sorry for my poor drawing here of it, right? But it would end up looping back around here, meaning that this is my North Pole, and this side must be my South Pole. Now, another circuit over here. It's actually the only thing different is the battery has been flipped, so current is flowing the opposite way. Here, the current comes out and then seems to go in front and then behind, in front, then behind. So I need to take my hand and somewhat awkwardly curl it the other way, right? Put my hand to where it comes over the top and then would dip down back and behind. And of course, what you would see with my thumb is that it would be pointing to the right whenever you do that as well. Try that out yourself, but the current comes out in front and then dips back and behind. So my thumb must be pointing to the right here. So magnetic field flows this way on the inside, and then of course as soon as it exits, just like a bar magnet, right? It would double back around the other way. Meaning this side is my north, and that side is my south.